I have a regret. That something has been with me for years. 13 years ago, I was one of the first to create an electronic system to stabilize a model rocket. What few people know is that thanks to that video, I started working on real autopilots. So I had to move far away from my amazing workshop. The regret I had all these years is that I was so busy that I never shared the details of this project. I'm Adriano Arcadipane, and after just 13 years, I have decided to tell you all about it. Back then, I had to choose a topic for my degree thesis. I thought to myself, I'm into rockets, I know how to program, and I enjoy building things. Why not take one of my models and create a system to stabilize its roll? Here's the plan. I had to take a rocket and add fins connected to a computer. The system would prevent the rocket from spinning during the ascent phase, and then the model would return to Earth safely with a classical dual deployment parachute system, as it always had. So I simply took an Arduino and found a ready-made example on the internet, but no, Arduino was invented only in 2005, so I had to do everything, but really everything, from scratch. Before we start, why should they stabilize the roll of a rocket? I'll explain it in simple words. So, with some simplification. A classic rocket is longitudinally stable, meaning it goes straight. This is because it has fins at the back, and when there is a disturbance, the airflow of the fins put it back in place. But there's nothing to prevent this movement, which is called roll. And any small imperfection, even just in the paint, will make it spin. To eliminate the spin, we need something allowing us to control it at will. Then we will have to maneuver just enough to generate a force equal and opposite to the disturbance. It's a bit like flying a plane with a crosswind. To go straight, you have to keep the rudder on its side. In my case, I used a pair of movable fins connected to a servo motor. The mechanism you see here ensure they always had the same angle. Choosing the sides and the shape of the fins, and then understanding their impact on the overall rocket stability was one of the most challenging things. And that's always the case when aerodynamics comes into play. For a deeper dive into this, go directly to my thesis. Here we can say that this electromechanical module is well made enough to maneuver the rocket, but it's not enough on its own. We need some electronics to make it intelligent. First of all, we need a processor that is the real brain of the rocket and runs the software. It connects to the servo, the small actuator that moves the fins, and to the sensors. The only sensor strictly necessary in this case is the gyroscope, which measures angular speeds. In our case, how fast the rocket is spinning. Actually, I also added other sensors, a high-G accelerometer and an atmospheric pressure sensor. By combining their data, can be obtained an acceleration, speed, and altitude. Those data are then recorded on a memory to be analyzed after the flight. The electronic design went smoothly, but then, during the assembly, strange things started to happen. The gyroscope had electrical contacts only on the bottom. It is made to be soldered with an industrial technique called reflow soldering, according to which the board pads are covered with a metal paste, the components are placed on the PCB, and then everything is put into an infrared oven, following a precise heating curve. Instead, I used a frying pan. Believe me or not, it worked. Who decides how to move the fins? The algorithm. So let's talk about software. At PowerUp, the software retrieves the calibration from memory, checks that all sensors are connected, and then patiently waits for liftoff. But how is liftoff detected? Initially, I used a condition on the flat speed. In this way, the launch was detected with a 200 milliseconds delay, which is too much. So I prefer to switch to a KISS method, which stands for Keep It Simple Stupid. Now the computer detects liftoff when the acceleration exceeds 2.5 Gs. In other words, when it gets it tired. Simple and effective. Once in flight, we enter the main loop. The main loop is the most important part of the software, and it is executed 100 times per second. Every 0.01 seconds, the software reads the sensors, reconstructs the state, and then sends this data to the control algorithm, which is a mathematical formula that chooses how much steer the fins depending on how the rocket is spinning. It's as if there was a real pilot there, able to perceive the altitude and maneuver accordingly. Specifically, I used the Kalman filter and the PID controller. And after some pretty tedious assembly work, here is the result. On the desk, it works, but what happened in real flight? My flight program consisted of 3 launches that would gradually bring me to have a full working system. Then, in reality, it took more, but we'll see that. First launch of the program was for general testing. Fins fixed it in the center and see what happens. The launch seems to have gone well, but there were several software problems. Despite having done a myriad of tests on the bench, the launch was detected late. The roll rate was not estimated correctly, and the gyroscope calibration strategy was a disaster. Once these problems were solved, I repeated the launch. This time went well. The data confirmed that the spontaneous rotation was in line with my theoretical calculations. I was happy. I thought, if the disturbance is as expected, my fins will work. Far from it. Second point of the program was check maneuverability. The flight consisted of taking off with the fins fully turned to the right and then turn them to the left in the middle of the flight. I expected the rocket to do the same. Instead, it went first to the left and then more to the left. Not good. Remember when I said that when aerodynamics comes into play, things get complicated? I was referring to this. Problem was that the fins couldn't handle it. I had 2 options. The first was to increase the deflection angle. I had set the maximum at 9 degrees, but seeing the flying log and doing some calculations, I concluded that 12 degrees would be needed. But at this angle, the lift produced is no longer directly related to the deflection, while the control algorithm expects a linear correlation. So, out of caution, I pushed option 2, makes the things bigger. After a few days, I was ready again. Time was running out, and I went straight to phase 3 of the program. All functions active, it make or break. Literally. The rocket takes off and the fin breaks off. There were just 3 weeks left, and I didn't want to go in front of the thesis committee to present a failure. Fortunately, the remaining part of the rocket had landed intact, so I went back to plane A. I mounted the previous fin set the maximum deflection to 12 degrees, and crossed my fingers. Another flight. We take off. There are some shade, but it works great. Did you notice what I noticed? Let's go back. The rocket leaves the ramp without rolling, then suddenly the lower section of the rocket rotates. What happened? The 2 sections of the rocket are held together only by friction, and with a little force you can make them slide. And that's exactly what happened. The upper fins produce a torsion in one direction, the lower ones in the other directions, hence the sudden rotation that the system was only partially able to counteract. Even so, the flight was a success. Can it be improved? Certainly yes. Analyzing the data carefully, you can see some problems. There's a delay in the action of the controller, and for much of the flight, the fins reach the end of their stroke, so even 12 degrees is not enough. Going to conclusions. I tried to keep this video short and easy to understand, but if you want to go deeper, you can find all the documentation, code, and diagrams on my GitHub profile. That's all for today. Thanks for watching.